question?
I'm afraid to take an IQ test though, because I feel like if I get like too low of a score, I just like feel stupid.
Hello and welcome back to Calculus 3, section 12.6, Directional Derivative and Gradient. 2 sections ago, we talked about partial derivatives, and I said that partial derivative in respect to x is the derivative in direction of x-axis, and partial derivative in respect to y is the derivative in direction of y-axis. But then, what if you want to go in a direction of line y equals x, or for that matter, any other line? So what we are going to learn now is to figure out how to introduce a vector in this notation so that we can have a derivative in a direction, in any direction. Imagine yourself on some kind of a sloped surface, like let's say you're hiking up the hill, up the mountain, right? And you are on a surface that curves and so on. You are programmed, your brain is programmed to look for most efficient way. Unless you are a professional rock climber and so on, right? You will not look for the steepest possible way to get up the mountain. You will be looking and you know, walking in a way that you are experiencing the lowest amount of incline. And we are just programmed that way. We evolved that way, right? Because we are trying to keep the energy consumption at the minimum so that we can store the reserves for later, right? Because food is supposed to be scarce. Well, now it's abundant. If you look at certain people, it's definitely confirmed, but like me. But then, you know, there is some period of 100,000 years, right, when the food was not abundant. You had to work very hard to get that food. So, is it possible to take the derivative in any direction? And the answer is clearly yes, because that is the title of our lecture today. So, directional derivative is going to be the vector of partial derivatives that it's multiplied in a dot product with the unit vector of the direction in which you want to measure the derivative in. So the directional derivative is actually the combination of partial derivative of x and partial derivative of y, and that is dotted with the unit vector. Now you have to be very careful. A lot of grade is lost in this course for you neglecting the fact that it has to be dotted into a unit vector. Derivatives measure change, and all of the change that you measure, all of the change is coming from the partial derivative of x and partial derivative of y. So you are not allowed to change that quantity, but you still have to dot this with a vector to get the direction out of the calculation. So that's why that vector better be a unit vector, because when you are multiplying something with a unit vector, you are multiplying the magnitude by 1, hence not changing the previous values. Yes?
Are we going to get a scalar out of that? You got it?
Yes, right? Because it's the slope of the, yeah.
Oh, okay.
Mm-hmm. So let's take a look at the formal definition, and then we are going to take a look at the formula that we are actually going to use to compute these things. So formal definition for directional derivative is, let f be differentiable at point A, B, and let vector u with components u1, u2 be a unit vector in xy plane. So in xy plane, then the directional derivative. So derivative in the direction of u of f at a and b is given by good old limit of the difference quotient. So limit h goes to 0, and now we have this f of a plus h times u1, comma b plus h u2. No, b, there's no h. B plus h u2 minus f of a b divided by h. So this is the official definition, but clearly, right, you would have to solve the limit. So that would not be the way to compute this. Instead, we use the theorem for the directional derivative. Which has the same statement as the upper one, but we just say that the directional derivative of f of at a, b in direction of vector u, and that is the unit vector, so I put the hat rather than the arrow, is going to be partial derivative in respect to x computed at a, b, comma, partial derivative of in respect to y of a, b, computed at a, b, dotted with the unit vector u1, u2. This is the formula that we are going to use to figure out directional derivative. So what are we going to do? Well, I want to say, have a function f of xy, say, given by 3x squared y minus e to the x y plus 6, and then I have a point 0, 3, and I want to find the derivative in, now please note my notation, derivative in direction of 1 and 6. So this is the standard setup for the problem where you have the function. Now function is giving you what? Function is going to give you some kind of a shape on which you can walk, right? It's giving you a surface. Now that surface is going to have the curved surfaces everywhere, and the derivative will measure how fast it's changing as you are walking in whatever direction you want to walk. So f of x is just giving us the top of the surface. Now we have a point at which we are standing, which is 0, 3 in this case, and then we have the directional vector 1, 6 is the direction in which we want to go. Now note my notation over there. My notation over there says u with the arrow. This is where your grade dies for this problem. This is not a unit vector. The magnitude of this thing is square root of 37. That's not 1. Square root of 37 is not equal to 1. So the first order of business that you have is to turn that u vector into a u hat, unit vector, and then you can go about and fix the rest of the problem using the formula above and be done in 5 seconds. Because you can all do dot product eyes closed. So u hat is equal to vector 1, 6 divided by square root of 37, which gives us 1 over root 37, 6 over root 37. This is the unit vector that we need. Unit vector. Liz, I'll need the charger because this thing just went into the gloom mode. Please don't forget to take it on your way out. Because I know what I'm going to do. Just put it in my bag. and then see you Monday. So, to compute the directional derivative, I need two partial derivatives. I need fx and I need fy. So fx is 6xy minus y e to the xy, and fy is 3x squared minus x e to the xy. So these are my derivatives. And as you can see in the formula, you're supposed to compute those partial derivatives at the point at which you are standing. So now I have to compute these partial derivatives at 0, 3, meaning every x is replaced by 0, every y is replaced by 3. So fx at 0, 3, 0 will kill the first term, and then all I'm going to have is negative 3 e to the 0. It's just negative 3, right? Yeah, e to the 0 is 1. Very good. And now fy at 0, 3 is 0, because x is 0 and kills both terms. So now, what do I have? Directional derivative in respect to u of f at 0, 3 is going to be vector negative 3, 0 dotted into the vector 1 over root 37, 6 over root 37. So directional derivative is simply negative 3 over square root of 37. Now, remember to rationalize, right? So we are going to go root of 37, root of 37, for the total of negative 3 root 37 over 37. And as you can see, the answer is scalar, as you wanted it to be. What is this? Well, this is the slope of the line, right? And that's that.
With the partial derivative and the normal derivative, they both find slope.
Mm-hmm.
What if like there wasn't a 0 to cross out? Would you just add the 2?
You would have more work to do. I picked one with the 0 because I also picked e to the x. So I really didn't want to compute e to the, 6, say, or something. So that's why I picked 0. I can bet that the textbook is filled with interesting examples for you to enjoy over the weekend.
What slope is that for?
Okay, so first off, you have to understand that the line that I'm talking about is a third-dimensional line, which should be a vector. Now, this is the magnitude of that, right? And the direction is given by the unit vector. So you can use those two concepts to actually create the vector, and then you can compute your function at 0, 3 for the x, 0, y, 0, z, 0, the same like an exam. And then you can actually come up with the equation of the line, which will be the tangent line, right? And that would measure the slope. So this number here measures the steepness, right? The larger the number, the steeper the slope, and then the smaller the number, the more flat. If the number is 0, we know it's a horizontal, right? So your xy plane has this number to be 0. Now that should make common sense because it's flat. So one more time, just to make sure, you see that the entire example has the one line that it's written in blood, red. And the reason is, if you are losing points for these problems, it's most likely there, because you are not being careful. You need that unit vector there. So just from a theoretical stand, the partial derivative of x and partial derivative of y are the ones that actually carry the slope. So that is how much of the slope is there. And then this vector here carries the direction with magnitude 1. So when you combine the derivative measures and the direction, you get the directional derivative. Now, this directional derivative can be done in 3D, 4D, 7D. We don't care what type of dimension you have because it's a dot product, right? Dot product works in all dimensions. Cross product works only in the certain dimensions, right? So that's another part that you might want to pay attention to. Now, the next part of this lecture is to give a special name to this part of the formula here. This part of the formula is going to be called the gradient. Gradient is a simply vector of partial derivatives. And we are going to use that one a lot. So you better know it. Otherwise, you are doomed.
What's it called again?
The gradient. So the gradient is a vector of partial derivatives. You want a 2D gradient? Not a problem. The notation is this upside down triangle with the arrow on top because it's a vector. And if you want the gradient of function f of x, right, is just going to be a vector partial of x, comma, partial of y. You want the 3D version? Not a problem. We go x, y, z now. And we have partial x, x, y, z, partial y, x, y, z, and finally partial in z of x, y, z. So there are your two-dimensional and three-dimensional cases. Now, the entire process is you being able to take partial derivatives, obviously. So let's do the example for this. Find gradient for age of x, y, z is equal to x, y, z minus sine y. That's all you need. Follow the formula. All right, so to find gradient, we simply find partial derivatives. That was enough time for you to come up with this thing. So partial derivative in respect to x is just yz. Partial derivative in respect to y is xz minus cosine y. And partial derivative in respect to z is just xy. And that's the gradient. If you need to compute this gradient at a point, you will just replace x, y, z from the point where they belong, and you will come up with a vector, I don't know, 3, 6, negative 5, whatever it is. Now that we gave the special name, we can recast our formula for directional derivative. Into simply gradient of f dot u. So this is the simpler formula for directional derivatives. Good effort. So now, very important part is this interpretation of the gradient, and we have a theorem that connects the gradient to the fastest way down, right? The steepest ascent and steepest descent. So the theorem 11 says the following. Well, directions of change, right? Let f be differentiable at AB with gradient of f of AB not being 0. Number 1. No, number 1. You can do ABC if you want to. Sure. So f has its maximum rate of increase. F has its max rate of increase at AB in the direction of the gradient. Delta FAB. The rate of change is the magnitude, right? So please remember that delta is a vector, right? So you will have some vector there, and then you take its magnitude, and that's, we already did this, but somewhere. Yeah, right here, magnitude. Number 2, f has its maximum rate of decrease. At AB in the direction of negative gradient of f at AB. I'm just hoping that these concepts are not, tripping you or something. This is the same as Calculus 1, guys. Your first derivative is positive, function is increasing, right? Well, what is the gradient vector? It's a vector of first partial derivatives. So technically, your gradient is equivalent to your Calc 1 first derivative. So in Calc 1, you have first derivative positive, you have increasing function. Over here, for the positive value, we have maximum rate of increase. And now with the negative gradient, we have the maximum decrease, right? So it's, and the rate is negative of f of AB. And then finally, the directional derivative is 0. In any direction orthogonal to the gradient. So directional derivative is 0 in any direction orthogonal to the gradient. Now I need to switch to the computer to show the image on page 921, I believe. Yep, 921. Please look at the two graphs of this elliptical paraboloid. So we have elliptical paraboloid, and it is ellipse now because there are different numbers in front of x squared and y squared. Hopefully you already moved past that point. That was in 12.1. If the numbers in front of x squared and y squared are the same, your paraboloid is a circle. If they have different numbers, that spells different radii, right? So it's ellipses. If you look at the level curve, right, you can find your directional derivatives, and directional derivatives will show direction of the fastest and the slowest. The fastest descent and the fastest ascent, and that would be these ones. So when you see here at this particular point, the blue one goes up, ascent, and the red one is down, descent. So guys, that literally translates to you are walking on the side of the mountain, which is the fastest way down and which is the slowest way up, right? Fastest way up, which is what's the steepest way to get down and what's the steepest way to go up. And then direction of the zero change in z, that would be orthogonal. So if you just cut the plane with the xy, right? Well, z equals a number, right? Anything that is orthogonal to anything that is orthogonal to the gradient, there we go, couldn't remember the word, gradient is going to give us zero change. Now, what that means is you are walking on the side of the mountain, you are not going up in Z, you are not going down in Z, right? You are walking along the side of the mountain. You can walk around the mountain if you want to, right? The trick is you're not going up, you're not going down. So that would be zero change, right? Zero change, let's say in Z direction. All right, so that's that part. Again, calculations is just, you know, to plug formulas in. Let me see if I can fish out a problem. We still have about 10 minutes left, so that's enough for an example. After this lecture, we are left with 3 sections, I believe, right? We have 8, 9, and 10. 7, 8, 9. Yeah, 7, 8, 9. Good.
7, 8, 9. That's my IQ just.
Mine just dropped.
Oh yeah. What's the pay point?
What happened?
Like an official IQ test. How much does it cost?
I think it's about anywhere from $200 to $400, and so I think 4 hours.
Really? Or do you know how dumb you are?
Yeah, you can take it that way. But, I mean, yeah. It is the only thing that will tell you that. Math grades are not going to tell you that because you can beat these tests. All right, so here is a problem. Let's take a look at problem 28, which addresses these things. So problem 28 says that the function, the surface, f of xy, is given as x squared plus 4xy minus y squared, and the point that we are looking at is 2, 1. So find the direction of the steepest ascent and the steepest descent. Well, they're right here. It's just the gradient at that point and negative gradient at that point. It's going to give us vectors, right? And then how fast it goes up and how fast it goes down, find the magnitude of those vectors. So fx is 2x plus 4y. Fy is 4x minus 2y. Fx at 2, 1. So if x is 2, we get 4 plus 4 is 8. Good effort. And then, again. Now, x, that's a 16 minus 2, which is 14. Great. So what I did is I found that the gradient vector, 4 times 4, oh, 4 times 2 is 8. Yeah, please pay attention. So gradient vector at 2, 1 is given by 8 and 6. Fastest ascent is going to be vector 8, 6, that's the direction, and then the magnitude, right, with magnitude square root of 8, so that's it says 10. Fine. I hear you loud and clear. There you go.
Whoa. Not
I'm sorry, I'm not using Apple products, so these things to me are nothing. So we have -8 and -6, and that would be now -10. It's a negative of the magnitude. Please note that the minus is in front of the...
Descending, right?
I'm sorry?
It's descending?
Yes. So that's why there is a minus in front. So this is like a slope of 10. You go 1 unit forward, but you went 10 units up.
So will they always just be opposites?
Yes.
Okay.
Always. Because it's at the same point. So only one kind of steepness exists at that point. Positive to go up and negative to go down.
Yes.
How many points off is it if we don't show our work with the
No points off. Why would points off? You want points off? Okay, fine. So only for Rob's exam, points off if he doesn't show the work for the descent. The rest of you are free not to show the work for descent. Just put the minus sign, yeah.
Nice.
Okay.
I will see you all in 4 days, right? On Monday.
Harder.
Yes. Bye.